Welcome to my YouTube channel. In this video, we are going to study backtracking algorithmic strategy. The name backtrack was first devised by D.H. Lehmer in the 1950s. Using backtracking, we can solve the problems which having multiple solutions. While using backtracking, we have to satisfy a complex set of constraints. In backtracking, we build a solution incrementally, one piece at a time, and backtracking for those solutions that fail to satisfy the constraints of the problem at any point of time. Let's try to understand how backtracking works with the help of example n queens. The n queens problem is a generalization of the 4 queens problem. The n queens problem is to place n queens on an n by n chessboard so that no two queens attack each other by being in the same row or in the same column or on the same diagonal. In this chessboard, I have kept the first queen in first column and first row. So we cannot put any other queens in the first row, in the first column and on the same diagonal. While solving this 4 queens problem, we put the queen in its own row. That means put queen 1 in first row, then keep queen 2 in second row, then place queen 3 in third row and fourth queen in fourth row. So here we have to assign only column numbers for the queens. At first we are keeping our first queen in first column. Then there will be no place in second column, first and second column for the second queen. So we are placing the second queen in third column. So applying all our rules, there will be no place for the third queen. So let's represent all those cases here in with the help of tree. We are keeping our first queen in first column. Then we cannot put our second queen in second column. So again backtrack here. Then place the second queen in third column. But there will be no place for the third queen. So again backtrack here. So while backtracking, we are moving this second queen into fourth place. So after that, there will be only one house for the third queen, that is the second column. But again, there is no place for the fourth queen. Here we are moving our second queen into fourth column. Then we will put our third queen into second column, but there is no place for the fourth queen. So again backtracking. There is no place for the third queen in third column. So again backtracking. So here we have to do the backtracking, but there is no place to move this second queen. So again backtrack and move this first queen to the second column. So we have moved here the first queen into the second column. Then we will move the second queen into the fourth column. Then there will be the only place for the third queen in first column. And we can keep here our fourth queen in third column. So this is the solution state. As No two queens are attacking here on each other. We are moving our first queen into the second column. We cannot keep our second queen in first column. We cannot keep second queen in third column also. So again backtrack here. There is a place for second queen in fourth column. Then we can move our third queen in first column and we can place our fourth queen in third column. So this is our solution. This is our answer state. It uses a simple depth first search on search tree. Depth first node with constraints is called here backtracking, and the desired solution is expressible as an n tuple x1 to xn. So in this tree, the tree traversal is like 1 to 2, 2 to 3. 3 is not satisfying the constraints, so we are calling it as backtracking. Then we are moving towards the fourth node, then fifth node. Again we are backtracking here. Similarly, in the whole tree we are traveling DFS, depth first search. And here desired solution is represented with the tuples x1 to xn. Here in this example it's a x1, x2, x3 and x4. Backtracking algorithms determine problem solutions by systematically searching the solution space for the given problem instance. So this is the solution space for the 4 queens problem. Here the similar tree can be added for the x1 is equal to 3 and x1 is equal to 4. Each node in this tree defines a problem state. So the nodes shown with here the yellow colors are called the problem states. All paths from the root to other nodes defines the state space of the problem. So all the paths from the root to the nodes are called the state space. Solution states are those problem states, yes, for which the path from the root to S defines a tuple in the solution space. Now let's see what is answer states. Answer states are those solution states, yes, for which the path from the root to S defines a tuple that is a member of the set of solutions and which satisfies the implicit constraints of the problem. So here this is the answer state. This solution state gives you the successful answer or it satisfies the all constraints, so that's why it's called the answer state. The solution space to the given problem can be represented with the help of tree-like structure which is called the state space tree. So this is called the state space tree for 4 queens problem. Once a state space tree has been constructed for any problem, this problem can be solved by systematically generating the problem states, that is all the nodes, determining which of these are solution states. Then we have to determine here the solution states and finally determine which solution states are answer states. That means we have to determine here the solution states which satisfies the all constraints, and those solution states are called here answer states. And all those answer states are the final solutions for that problem. Problem solvable by backtracking. We can solve the problems: n-Queen's problem, sum of subset, graph coloring, Hamiltonian cycles, knapsack problem, and number of puzzles like Sudoku, night tour, tic-tac-toe, maze problem. Here I have referred the book Fundamentals of Computer Algorithms. Thank you friends. For any queries, please write it into the comment. If you like this video, then press like button. To see more videos, subscribe to my YouTube channel. Thank you.